In this video, I want to look at unit vectors and general vector properties. If I'm given vectors v is equal to the vector described by the components v sub 1, v sub 2, and the vector u is described by the components u sub 1, u sub 2, and I'm given a scalar c, then vector addition can be expressed as the vector v plus the vector u will be equal to a vector that has the components v sub 1 plus u sub 1 and v sub 2 plus u sub 2. Vector subtraction can be expressed as the vector v minus u is equal to the components v sub 1 minus u sub 1 and v sub 2 minus u sub 2. Scalar multiplication can be expressed as c times the vector v is equal to a vector with the components c times v sub 1 and c times v sub 2. Vector operations are just operations that involve working with the components for each vector. But remember that this presumes that the base of my vector is placed at the origin with components 0, 0. The magnitude of my vector is the length along the vector from the origin to the tip of the vector. A vector v expressed by components v sub 1, v sub 2 will therefore have a magnitude given by placing the vector v inside absolute value bars and letting that be equal to the square root of the quantity v sub 1 minus 0 squared plus v sub 2 minus 0 squared, which becomes just the square root of the first component squared plus the second component squared. A vector with a magnitude of 1 is called a unit vector. Let's work a couple of examples. I'm given 3 points, O with the coordinates 0, 0, P with the coordinates minus 4, 3, and Q with the coordinates 7, 6. I want to find the components and magnitudes of the vectors from O to P and from P to Q. The vector from O to P is given in component form by the vector OP is equal to the component vector minus 4, 3. The magnitude of the vector OP is given by the absolute value of the vector OP is equal to the square root of the quantity minus 4 minus 0 squared plus the quantity 3 minus 0 squared. This is just the square root of the sum of 16 and 9, which is just equal to 5. For the vector PQ, this vector in component form is going to be given by the vector PQ is equal to the components of 7 minus a minus 4 and 6 minus 3. In other words, I subtract the first vector's components from the second vector's components, and I get a final component vector given by 11, 3. The magnitude of this vector PQ is given by the absolute value of the vector PQ is equal to the square root of 11 squared plus 3 squared. This is the square root of 121 plus 9, and I'll leave that as the square root of 130 so that I have it in exact form. Now I want to work a second example. Given the same 3 points with O having coordinates 0, 0, P having coordinates minus 4, 3, and Q having coordinates 7, 6, I want to find unit vectors for each of the given vectors. My vector OP we found had a magnitude of 5 in the earlier example. A unit vector is simply found by dividing the original vector by its magnitude, so that the unit vector is given by the vector OP divided by the magnitude of the vector OP. That in component form looks like the components minus 4, 3 over 5. I'm going to write this in vector component form with I hat and j hat. This gives me minus 4 I hat plus 3 j hat divided by 5. I break it up into separate components, and my vector is given by minus 4/5 I hat plus 3/5 j hat. For the vector PQ, we found that the magnitude was a square root of 130. My unit vector will be given by the vector PQ divided by my magnitude. This means my component vector 11, 3 divided by square root of 130 is my new unit vector. I write it in vector component form with I hat and j hat. 11 I hat plus 3 j hat divided by the square root of 130. I break it up into specific components. My unit vector is given by 11 over square root of 130 I hat plus 3 over square root of 130 j hat. I want to work another example. If I'm given the point P with the coordinates -3, -6, and the point Q with the coordinates 5, 9, I want to find the following. I want to find the vector PQ and give two unit vectors that are parallel to PQ. Then I want to find two vectors of length 3 that are parallel to PQ. I first need to express the vector from P to Q. This will give me a vector with components 5 minus -3 and 9 minus -6. In component form, this is the vector with components 8, 15. In I hat, j hat form, it's the component vector I hat plus 15 j hat. Now I need to know the magnitude of my vector. This is given by the square root of 64 plus 225, which is equal to the square root of 289 and simplifies to 17. One unit vector that is going to be parallel to PQ will be given by the vector PQ divided by the magnitude of PQ. The vector PQ divided by the magnitude of PQ gives me the vector 8i hat plus 15j hat, all divided by 17. In vector component form, this becomes 8/17 I hat plus 15/17 j hat. A second unit vector, parallel to PQ, is very easy to find. I simply multiply the unit vector we just found by -1. This is parallel, although it points in the opposite direction, but this is really the easiest one to find. This gives me -8/17 I hat minus 15/17 j hat. Now I want to find two vectors that have a length of 3 that are parallel to PQ. Sticking with my theme of keeping things simple, I'm just going to recognize that one vector parallel to PQ with a length of 3 will be given by multiplying my unit vector that we just found by 3. 3 times my original unit vector gives me 27/17 I hat plus 45/17 j hat. The second unit vector with a length of 3 and parallel to PQ is going to be the negative of that vector. So I'm going to get -3 times PQ over the magnitude of PQ, which is equal to -27/17 I hat minus 45/17 j hat. We have some properties of vectors that I want to mention. These are properties you know very well. They're the same properties that we have in algebra. I have a commutative property of addition, which means I can add my vectors in any order I choose. There's an associative property of addition, which means I can group two vectors together before adding the third, and I can group them in any order I choose. There's the additive identity. If I add 0 to a vector, I get the same vector back. There's the additive inverse. If I add a vector to the negative of that vector, I get the 0 vector. There's the distributive property, where I distribute a scalar to two or more vectors that are being added together. And there's the distributive property, where I may distribute a vector to two scalars that are being added together. There's the multiplication by a 0 scalar, which gives me the 0 vector, and there's the multiplication by a 0 vector, which gives me a 0 vector as well. I have the multiplicative identity. If I multiply 1 times any vector, I get the vector back. And I have the associative property of scalar multiplication. In other words, a scalar multiplied times a scalar multiple of a vector is the same thing as multiplying the two scalars and then multiplying that product by the vector itself. Let's work another example. I want to solve 3 times the vector u plus 4 times the vector v is equal to 12 times the vector w, and I want to solve this for v. And I'm going to use the basic principles of algebra that we've always used for equations. I'm going to subtract 3 times the vector u from both sides. I get 3 times the vector u plus a -3 times the vector u plus 4 times the vector v is equal to 12 times the vector w plus -3 times the vector u. 3 times the vector u plus -3 times the vector u gives me the 0 vector. This means that I'm left with only 4 times the vector v, and I'm going to multiply both sides now by 1/4 in order to solve for the vector v. I find out that v is equal to 3 times the vector w minus 3/4 times the vector u. So now you get to try it. Pause the video, and for the vectors u is equal to 2 I hat minus 7 j hat, the vector v is equal to minus 4 I hat plus 9 j hat, and the vector w is equal to I plus 2j, Find the vector u minus 3 times the vector v plus 2 times the vector w. Then find the magnitude of 2 times the vector u plus the vector v minus the vector w. And then give two unit vectors that are parallel to the vector u minus 3 times the vector v plus 2 times the vector w. When you're ready, restart the video to check your understanding. So for the first one, I want to find the vector u minus 3 times the vector v plus 2 times the vector w. I simply plug in the vector component form for each of my vectors, and I get 2i hat minus 7j hat minus 3 times negative 4i hat plus 9j hat plus 2 times I hat plus 2j hat. I'm going to use my distributive property and collect like terms. The like terms will be all the I hat terms and all the j hat terms. I get 2 plus 12 plus 2 I hat plus negative 7 minus 27 plus 4 j hat. This reduces to 16 I hat minus 30 j hat. In the second one, I want to find the magnitude of 2 times the vector u plus the vector v minus the vector w. The first thing I have to do is determine what the vector is that I'm actually finding the magnitude for. So I'm going to work inside the absolute value bars. I'm finding the magnitude of 2 times the vector 2i hat minus 7j hat plus the vector negative 4i hat plus 9j hat minus the vector I hat plus 2j hat. Again, I use my distributive property and collect like terms. This becomes the magnitude of the vector 4i hat minus 14j hat plus the vector negative 4i hat plus 9j hat plus the vector negative I hat minus 2j hat. I collect the like terms. I'm looking for the magnitude of 4 minus 4 minus 1i hat plus negative 14 plus 9 minus 2j hat. In other words, I'm looking for the magnitude of the vector negative I hat minus 7j hat. That magnitude is equal to the square root of negative 1 squared plus negative 7 squared. That's the square root of 50, which reduces to 5 times the square root of 2. For my last problem, I want to give two unit vectors that are parallel to the vector u minus 3 times the vector v plus 2 times the vector w. This one is something we just worked. The expression reduces to 16 I hat minus 30 j hat. Now I need the magnitude to find a unit vector. The magnitude of this vector is given by the square root of 16 squared plus 30 squared, which is 34. So my first unit vector that is parallel to the given vector is given by 8/17 I hat minus 15/17 j hat. Now, keeping things simple, all I have to do to find a second unit vector parallel to the given vector is to multiply through by negative 1 and change its direction. If the direction changes, the vectors are different. This means that my second unit vector that's parallel to the given vector will be given by negative 8/17 I hat plus 15/17 j hat. This has been a quick review of working with vector properties. Be sure and let me know if you have any questions.